Welcome back to the deep dive. We're digging into the sources you shared, and today it's all about a really fascinating challenge in video, creating realistic sound.
Yeah, not the dialogue, not the music score, but everything else. Footsteps, doors closing, rain, what filmmakers call Foley.
Exactly, and the goal here is generating that Foley automatically from the video itself, which sounds simple, but it's actually incredibly difficult.
It really is. You need two key things. First, the sound has to semantically match what you're seeing. So if you see rain, you need to hear rain sounds. That's sort of the baseline.
Okay, makes sense.
But the really tough part is the timing, that splash you see. The sound needs to hit at the exact same millisecond. Humans are amazing detectors of sync issues. We can apparently spot mismatches as tiny as 25 milliseconds.
Wow, 25 milliseconds, that's incredibly fast, faster than a blink.
Yeah, it's a tiny window, get it wrong, and the whole thing feels off, unnatural.
So today, using the notes, the study guides, and that research paper you sent over, we're going deep on MMAudio. This is a new framework that's trying to, crack this code, right?
That's the plan. MMAudio aims to generate high-quality, precisely timed Foley directly from video, sometimes even using text prompts for guidance.
Okay, so how did these researchers manage it? How do they build something that learns both the what and the when of sound, especially given the problems earlier methods had?
Right, let's talk about those earlier problems first. What was holding things back?
Good idea. Lay the groundwork.
Well, the sources highlight a couple of big ones. First up, data. Or rather, the lack of good audiovisual data.
You mean video clips paired with the exact sounds happening in them?
Exactly. There are data sets like VGG sound, sure, but it's only about, 550 hours total? That's not huge in the world of deep learning.
And I bet it's not all clean data either.
You got it. It's often noisy. You get background music bleeding in, people talking over the action, sounds that aren't actually caused by what you see on screen, non-diegetic sounds.
Right. So trying to train a complex model from scratch on that limited, messy data, it's an uphill battle.
Definitely. You can't just feed it random web videos and hope it figures out that this footstep sound goes with that foot visually.
So what was the other approach people tried?
Well, they looked at those big, powerful text-to-audio models. Models trained on massive amounts of audio paired with text descriptions. Think data sets like WaveCaps, which has thousands of hours, much more data there.
Okay, so leverage that knowledge.
That was the idea. They tried to sort of bolt on extra modules to these pre-trained text-to-audio models. These extra bits would try to use the video information to guide the sound generation.
But it sounds like that wasn't ideal either.
Yeah, the paper suggests it often led to clunky, overly complex systems. You know, trying to force an engine designed for text into understanding video, it doesn't always integrate well. It might not adapt smoothly to all the diverse things happening in a video.
Got it. So MMAudio needed a different approach. How do you get that deep sight-sound connection and the perfect timing without the data limits or the architectural mess?
And this is where their first big idea comes in. They call it the multimodal joint training paradigm.
Okay, multimodal joint training. Break that down.
Fundamentally, instead of separate models or complex fine-tuning, they built one single network, a multimodal transformer designed from the start to handle video, audio, and text together.
One network to rule them all.
Sort of, and the real cleverness is how they trained the single network. They didn't just use the limited video-audio data.
They brought in the text-audio data, too.
Exactly. They jointly trained it on both. So the 550 hours of audio-visual data from VGG sound, plus those big audio-text data sets, WAV-caps, audio-caps, Clotho, adding up to around 7,600 hours of audio-text data.
Whoa, okay. That's a huge difference in scale. Like more than 10 times the amount of audio-text data compared to audio-visual.
Right, and that's critical.
But wait, if the network is designed for video, audio, and text, what happens when it only gets audio and text? How does it handle the missing video part during training?
That's a neat trick they used. When the model gets an audio-text pair, the input slots where the video features would normally go are filled with special placeholder tokens. These are learnable, so the model figures out how to essentially ignore the missing video, but still process the audio and text effectively.
So it learns to work with whatever combination of inputs it gets.
Pretty much. It learns to connect concepts across modalities, even if one is missing in a particular training example.
Okay, so what are the big wins from doing it this way, this joint training? Why is it so powerful?
The sources list several key benefits. First, data scaling. This is huge. By bringing in all that readily available audio-text data, They bypass the bottleneck of scarce audio-visual data. The model gets exposed to a much, much wider variety of sounds and the words used to describe them.
So even if it hasn't seen a specific type of explosion many times, if it's read about it and heard examples linked to text descriptions, it can figure out the sound better.
Precisely. Which leads right into the second benefit, a unified semantic space. Because it's learning from video, audio text, and sometimes video audio text altogether, this single network builds a shared understanding. Concepts link up across modalities.
Meaning the idea of dog barking learned from text-audio pairs helps it recognize and generate the right sound when it sees a dog barking.
Exactly. The semantic understanding transfers. It learns, as the paper puts it, richer semantics from more diverse data. The text kind of acts as a bridge.
That makes intuitive sense.
Yeah.
And did it actually work? Did they see improvement?
Oh yeah, big time. The empirical results showed major gains compared to training without the audio text data. Things like a 10% lower Frechet distance score that measures audio realism, a 15% higher IS score for audio quality, and critically a 14% better score on temporal synchronization just from this joint training approach alone.
So that joint training is really the foundation here. It tackles the data problem and helps it learn the meaning connection.
Absolutely. But we still have that timing problem, right? That super precise 25 millisecond sensitivity. Joint training helps, but getting timing perfect is another level of hard.
Right. Even with a good semantic understanding, the standard ways models link vision and audio, like cross-modal attention, can sometimes be a bit fuzzy on the exact timing.
Exactly. Sometimes that attention mechanism can hamper precision, as the paper notes, so they needed something else.
Enter innovation number 2.
We got it. The conditional synchronization module.
Okay, and this module has one job.
One very specific job. Achieve much more precise audio-visual synchrony. Nail the timing.
How does it do that? What's the mechanism?
It starts by extracting visual features that are highly relevant to timing. They use a separate pre-trained tool called SynchFormer for this.
Informer. What does that do?
Interestingly, SynchFormer is trained specifically to detect audio-visual misalignment. So its visual component becomes really good at noticing the visual cues that signal precise timing, sudden movements, impacts, things that need a sound right now. And they extract these features at a high frame rate, 24 fps, for temporal detail.
Ah, so they borrow a timing expert's eyes, essentially.
Yeah.
What happens with those timing features then?
They don't just get lumped in with the general visual information. Instead, they are processed and then carefully injected into the layers that are generating the audio, specifically into adaptive layer normalization, or ADLN, layers within the audio stream.
Okay, injecting timing cues into the audio generation.
And here's the crucial part. This injection, this conditioning, isn't applied globally across the whole audio clip. It's applied per token.
A token. So like at a very fine-grained level, frame by frame almost.
Think of it that way, yeah. Frame-aligned conditioning. It allows the visual timing cues to influence the audio generation for tiny slices of time, giving incredibly fine control over when sounds start and stop. Much more precise than just applying one general timing adjustment to the whole sequence.
Right, compared to just saying, make this whole clip feel generally in sync. This is like adjusting every single beat.
Exactly. And the results were stark. Adding this module gave them a reported 50% relative improvement in synchronization score.
50%. Just from that module focused purely on timing, that's huge.
It really underscores how vital that precise synchronization is and how specialized mechanisms can make a big difference.
So those are the two really big conceptual leaps. Joint training for semantics and data scale, and the sync module for timing precision.
Were there other smart architectural choices that helped pull it all together?
Yeah, the paper mentions a few other things that contributed. The overall network structure, for instance. It uses a series of blocks where all modalities interact, followed by blocks that are audio only.
Why split it like that? It lets them build a deeper network overall. Deeper networks are often better at generation tasks, but without forcing every single layer to process the complex multimodal inputs, it's more efficient. The model sort of figures out the cross-modal relationships first, then refines the audio generation.
Makes sense. Efficiency is good. What else?
They used something called aligned rho-PE positional embeddings. This sounds technical, but it's basically a clever way to handle the fact that the video input runs at a different speed, or frame rate, 8 fps, than the audio output, 31.25 fps.
Ah, aligning different clocks, essentially.
Kinda, yeah. It helps the model understand the temporal relationship between visual events and audio events, even with those different frame rates, contributing to better sync.
Okay, another piece contributing to timing. Anything else structural?
One more. Instead of standard MLOP layers in parts of the network, they use something called conv MLPs, which use 1D convolutions.
Conv MLPs.
Yeah.
What's the benefit there?
The idea is that these convolutions are better at capturing local temporal structure. Think about sounds that happen in quick succession, like footsteps or maybe drumming. These layers help the model better understand and generate those rapid, fine-grained temporal patterns within the audio.
So not just the big sync points, but the little details in the rhythm and timing of sounds too.
Exactly. And the ablation studies later confirmed this choice helped, especially with synchronization.
Okay, let's talk training then. We know what data they used VGG sound for AV, wave caps, and others for AT. How did they actually make the training work with these different types?
We touched on it, but the key was handling those missing modalities using the learnable empty tokens. That's what enabled the joint training on mixed datasets. They were also really careful, as the paper notes, to scrub the test sets, remove any examples that might have accidentally shown up in the training data. That's crucial for fair evaluation.
Good scientific practice. And how does the model actually generate the sound at test time?
They use a technique called conditional flow matching. It's a bit technical, but the high-level idea is the model learns to define a velocity field, or a path that can transform random noise into the specific audio waveform you want, guided by the video and maybe text input.
So it learns a recipe to turn static into sound, based on the video.
That's a decent analogy, yeah. It's a powerful generative technique. They also use something called classifier-free guidance. By sometimes hiding the video or text during training, they gain the ability at inference time to control how strongly the video or text guides the generation. Gives you flexibility.
Right. You can maybe dial up or down the influence of the text prompt, for instance.
Exactly.
So the moment of truth. All these innovations, careful training.
Yeah.
How did MMAudio actually stack up? What did the tests show?
The results, according to the paper, were really strong. They used a whole battery of objective metrics, things like FD and KL divergence, to measure how similar the generated audio distribution is to real audio. IS score for quality. An image-bind-based score for semantic alignment does the sound match the visual meaning, and several metrics for temporal alignment, like desync scores and onset-offset accuracy, and the outcome. Across most of these metrics, MMAudio set a new state-of-the-art among publicly available models on the standard VGG sound benchmark.
Wow. And that includes even their smaller model, the 157 million parameter one.
That's right. Even the relatively small MMAudio model was outperforming prior public methods, and it was pretty quick. Generating 8 seconds of audio took just over a second on their hardware.
Impressive efficiency. Now, you mentioned one metric, image bind score, where another model, seeing hearing, was slightly higher.
Yeah, good memory. Seeing and hearing did edge it out slightly on that specific semantic score. But the MMAudio paper points out that seeing hearing uses test time optimization specifically for that metric. MMAudio achieves a very high score without that, and outperforms seeing hearing overall, especially when you consider the other metrics and the user studies.
Okay. So context matters there. What about those user studies? Objective scores are one thing, but did people actually prefer the sound?
That's often the ultimate test, isn't it? And yes, the human listeners confirmed the objective findings. In head-to-head comparisons, users rated MMAudio's generated audio significantly higher for overall quality, for how well the sound matched the video content, semantic alignment, and for how well timed the sounds were, temporal alignment.
So the numbers translated into a genuinely better perceptual experience.
It seems so. That human validation is really important.
And there was that surprising result on text-to-audio generation, too.
Right. This really speaks to the power of the joint training and that unified semantic space. Even though MMAudio wasn't primarily designed or fine-tuned for just text-to-audio, it performed very competitively against dedicated TTA models.
How competitively?
It achieved state-of-the-art scores on metrics like CLAP score, which measures text-audio semantic similarity, and IS score for audio quality, compared to other TTA models evaluated on standard benchmarks.
That's pretty remarkable. A side effect of its main goal, almost.
It really demonstrates that the multimodal understanding it built is deep and transferable. It learned the sound concept links so well that it could apply them effectively even without the video cue.
Fascinating. And then there was the comparison to the behemoth movie gen audio.
Yeah, the Google model.
Yeah.
Much larger, trained on vastly more private data, reportedly over 100 times more video hours.
So David versus Goliath, how did MMAudio fare?
Amazingly well. In subjective user studies comparing MMAudio, their largest public model, about 1 billion parameters, to movie gen audio, 13 billion parameters. Users rated them as comparable on audio quality, semantic match, and even temporal alignment.
Comparable, despite the huge difference in scale and data.
Yes, and even more impressively, on some objective timing metrics like the desync score, and also in the subjective ratings specifically for temporal alignment, MMAudio was actually rated slightly better than Movie Gen Audio.
That's incredible. So while the giant private model might have an edge on really obscure sounds due to its data.
Plausibly, yes. The paper mentions an example with mashed potatoes where Movie Gen Audio might do better.
But for the core task of generating well-timed, appropriate sounds, MMAudio, built with public data and smart design, is right there, or even slightly ahead on timing.
It's a powerful testament to their approach. Smart architecture and training paradigms can really compete with brute force data scaling.
Which brings us to the ablation studies. You mentioned these earlier, proving that the innovations actually caused the improvements.
Exactly. Standard practice and research, you systematically remove or change parts of your system to see what breaks or gets worse.
So what did they find when they started taking MAudio apart?
The results strongly validated their key ideas. When they tested joint training by removing the text modality entirely, or removing all the audio-text data performance tanked across the board, realism scores got worse, quality scores dropped, and critically, the synchronization scores suffered.
So that proves the multimodal data, especially the text audio part, wasn't just a nice to have, it was essential.
Absolutely fundamental. Training on just the limited audio-visual data led to overfitting and much poorer results.
What about the conditional synchronization module?
They compared using their specific module against simpler methods, like just adding the timing features into the main visual stream or removing them altogether. The results were clear. Their dedicated module design achieved significantly better temporal alignment, the lowest, meaning best, desync scores.
Validating its specific role in precision timing.
Precisely. And the aligned rope embeddings, same story. Comparing aligned rope E against no positional encoding or non-aligned versions showed that the aligned versions specifically improved audiovisual synchrony, reducing the desync score.
So that detail mattered for timing too. And the conv-MLPs?
Yep, they tested that too. Replacing their conv-MLPs with standard MLP layers resulted in worse overall performance, notably including worse synchronization scores. This supports their hypothesis that the conv-MLPs are better at capturing those fine-grained local temporal patterns in the audio.
It really sounds like each of their core innovations was pulling its weight.
The ablation studies paint a very convincing picture that way, yes. The specific combination of joint training, the sync module, aligned rope P, and conv-MLPs is what led to the state-of-the-art performance.
Okay, so it's a very impressive system. But, as always, no model is perfect. What limitations did the researchers themselves acknowledge?
They were upfront about a couple things. The biggest one is generating human speech.
Right, you mentioned it produces unintelligible mumbles.
Yeah. Their thinking is that human speech is just a whole different ballgame. It involves complex language, grammar, intonation, speaker identity, things far beyond the scope of general environmental sounds or Foley effects that MAudio was focused on.
So it's not designed for dialogue, and it shows. Makes sense.
You'd still need dedicated speech synthesis models for that. The other limitation they mentioned relates to performance on concepts not well represented in its training data.
The mashed potatoes example again.
Kind of. Because MAudio is trained on public data sets, even large ones, there might be specific objects or actions that just don't appear very often. Compared to a model like Movie Gen Audio, trained on potentially much more diverse, even if private data, MMAudio might struggle more with those rarer edge cases.
So data coverage is still a factor, even with clever training strategies.
It seems so. Even with the smart scaling via text audio data, the specific visual concepts seen during training still matter.
Okay, so wrapping this all up, what's the big picture takeaway from our deep dive into MMAudio?
I think the core message is that MMAudio really pushed the boundary for video-to-audio synthesis. It set a new standard, especially for public models, by directly addressing the core challenges.
Those being data scarcity and timing precision.
Exactly. And it tackled them with two main innovations. First, that multimodal joint training, using text audio data to massively scale up the learning and build a unified semantic understanding. And second, the conditional synchronization module, laser-focused on getting that crucial temporal alignment just right.
And validated through metrics, user studies, and those revealing ablation studies.
Right, it's a strong piece of research, and it leads to that really interesting final thought the authors proposed.
The one about multimodality being key for synthesis in any modality.
Yeah. They suggest that maybe the best way forward for generating any kind of complex data images, video, text, sound, you name it, isn't just bigger models in one area, but models that learn the rich connections between different types of information. MAudio, they argue, lays some foundational groundwork for that in the audio, video, text space.
That is a provocative thought.
Mm.
It suggests a future where AI creativity comes from understanding the world through multiple senses, just like humans do. Definitely something to chew on.
Indeed. A powerful idea for where this field might be heading.